Okay, welcome back. In this video, we're going to talk about a couple of concepts that we covered in first year chemistry, but I wanted to review them again because they're so essential. The first topic is the mole. We're going to talk about what a mole is and how to convert from moles to particles to grams. And then we're going to talk about stoichiometry, another very important topic in chemistry. So I hope you got your guided notes out, you're following along, and let's get started. So a mole is an SI base unit used to measure the amount of a substance. It's abbreviated MOL. And a mole in chemistry is a number. So just like a dozen corresponds to a number, so does a mole. Like a dozen means 12. Okay? And a gross is a dozen, so that's 144. A ream, like a ream of paper, that would be 500 pieces of paper. Well, a mole in chemistry equals a number, and everybody should know it. It's 6.02 times 10 to the 23rd. That's a very famous number in chemistry. In fact, it's given its own name. But 1 mole equals 6.02 times 10 to the 23rd particles. And there's exactly 12 grams of carbon-12 in 1 mole of carbon, so that's like the standard. So 1 mole equals 6.02 times 10 to the 23rd particles. Well, what is a particle? A particle in chemistry can mean a lot of things. So it's kind of a generic term for atoms, for molecules, for compounds, ions, or formula units. So if you're talking about any one of these, we can just generalize it with the word particle. And so let's talk about that number again, 6.02 times 10 to the 23rd. It's so famous, it's given its own name. It's called Avogadro's number. It's called Avogadro's number in honor of the Italian chemist Amedeo Avogadro. And he was a chemist that figured out that if you had 1 mole of substance, that there was 6.02 times 10 to the 23rd particles of that substance. And so that's Avogadro's number. Okay, I've given each of you a roadmap. If you remember, I called this diagram the roadmap last year. This is just half of the roadmap. So we're going to kind of review this half. And we're going to do some conversions here. We're going to go from particles to moles. And we're also going to go from moles to particles. But I want you to pay attention to the arrows. If we're at moles and we want to go to particles, we got to cross this top bridge. Well, across this top bridge is a conversion factor. It's Avogadro's number on top divided by 1 mole on the bottom. And notice if you're at particles and you want to go to moles, you got to take this bottom bridge. And what happens to our conversion factor? Well, it's just flipped. So it does matter which way you're going across this roadmap. So we're going to go through a couple of example problems right now and look at how to convert from particles to moles and vice versa. Practice problem number 26. It says, calculate the number of molecules in 11.5 moles of water. When I do chemistry problems, I kind of have a systematic approach to doing these kinds of problems. And so we're going to go through the steps that I use to solve them, and hopefully you will follow them and that they will work for you. What I always do is underline what they give us. So like, for example, in this problem, they gave us 11.5 moles of water. And I circle what it is they want us to find. And that's the number of molecules of water. Okay? Now, I would like each of you to get a roadmap out. Okay? We are at moles. So look at moles. And now we want to go to molecules. Well, where's molecules? It doesn't say molecules on this roadmap. Remember, that's a particle. So molecule is a particle. So we're going to go from moles over to particles. We need to cross that top bridge on the left if you're looking at the roadmap. Okay, my second step that I will do is write down what they gave us. So 11.5 moles of water. And notice, I'm not just writing down the number. I also write down the units, moles, and what we're talking about, water. Okay, I write that down and put it in parentheses like that. I put it over 1 in that it's going to line up the rest of the conversion factors across our page. So we're at moles. If you look at the roadmap, we're going to cross that top bridge. Okay, but even if you didn't have a roadmap, if moles of water is on top, we know that moles of H2O has got to go on the bottom. In 1 mole of water, there's 6.02 times 10 to the 23rd molecules of H2O. Okay, so always write down the number and the unit. Now if we look here, moles of water divided by moles of water cancels out. Anything divided by itself is 1, so we can cancel that out. Okay, and now I'm to molecules of water, and I can stop there because that's what the problem was asking me to solve for. Okay, so you need a calculator. Please get a calculator out, and let's go through the answer. So how do you solve this? Well, you take the top number and you times it by the other top number, so you just times across the top, and that number is going to go on top. Then you're going to times across the bottom. 1 times 1, of course, is just 1, so that one's easy. So 11.5 times 6.02 e to the 23rd. And I get this number, 6.92 times 10 to the 24th. Okay, and any number divided by itself is just 1, so that's 6.92 e to the 24th is my answer. But I also need to write the units. The units that you're going to end up with are on top, so that's molecules of H2O. Okay, so if we look at what we just did, if you start with 11.5 moles of water, you're going to have 6.92 times 10 to the 24th molecules of water. Okay, let's go to practice problem number 27. This one's a little bit harder, more difficult, but I'm still going to use the same approach. So let's read it. It says, calculate the number of oxygen atoms in 5 moles of oxygen molecules. Oxygen is a diatomic molecule, O2. Okay, so let's underline what it gave us. It gave us 5 moles of oxygen, and it wants us to come up with the number of oxygen atoms. So oxygen atoms is what we circle. And what makes this problem just a little more difficult is that you have to know the difference between O2 and just simply an oxygen atom. So this one, oxygen, is an atom. It's one single atom. Where you have O2 here, now this is called a molecule. There's more than one atom bonded together there, so it makes a molecule. Okay, so we got to be careful. We want to go directly to not molecules, but we want to go to oxygen atoms here. But we're going to set it up the same way we always do. What I underlined there, what they gave us, is 5 moles of oxygen, which is O2. Put it over 1. Okay. Now let's look at the roadmap. I am at moles, and I want to go to molecules because O2 is a molecule here. And so let's do that. If moles of O2 is on top, I better have moles of O2 on the bottom. In 1 mole of O2, there's 6.02 times 10 to the 23rd molecules of oxygen. Molecules of O2. And so, yeah, here's the point that I was trying to make earlier. This is O2, so we couldn't go directly to atoms with O2 because O2 is a molecule. So we have to first go to molecules. But now my moles of O2 is going to cancel out, and I'm left with molecules of O2. But if you read the question carefully, it just wants us to calculate the number of oxygen atoms. And so I'm going to make one more conversion factor here. If molecules of O2 is on top, it's got to go molecules of O2 on the bottom. In 1 molecule of O2, how many oxygen atoms are there? Well, there's 2. Okay, now my molecules of O2 is canceled out. And now I'm at oxygen atoms, which is where it wanted me to go to, so I'm done. Throw in an equal sign. Now let's times across the top. So 5 times 6.02 e to the 23rd times 2. And I'm getting 6.02 times 10 to the 24th. If you look at the bottom, it's 1 times 1 times 1. So the bottom is just 1, so I don't need to write it. I also need to include my units here, so it's oxygen atoms. Okay, very good. I threw in some extra practice problems if we needed to, but for the sake of time and keeping these videos a little bit shorter, we're not going to go over them in the videos, but if you need to in class or if you need extra help, come in and we can solve them. So I'm just going to kind of skip through them right now. Oops. Okay, so now we're going to talk about another conversion that we'll always be asked to do, and that's from mass to moles, or we could go the other way around and go moles to mass. Now again, it does matter. If you're at moles and you want to go to grams, you have to cross this top bridge. And if you're at grams and you want to go to moles, you got to cross that bottom bridge. And now look at this new conversion factor we have here. It's molar mass over 1 mole. And on the bottom we have just its inverse, 1 mole over molar mass. So we need to know what molar mass means before we can do any of these conversions. So let's look at molar mass. Molar mass is the mass in grams of 1 mole of any pure substance. The molar mass of each element is given on the periodic table. So if we want to know an element's molar mass, we just look at the periodic table. Its atomic mass is its molar mass. For example, if we wanted to say we're looking for, magnesiums. What is magnesium's molar mass? Well, we look at the periodic table, and it's 24.3051. I always round to the nearest whole number with molar masses. So 24.3 is just going to stay 24. That's going to be 24 grams per mole. Okay, so always round to the nearest whole number. I guess if you don't round, you're more precise, but just to save all those decimal places, we're going to round it. All right, to find the molar mass of a compound or a molecule, simply add up the molar mass of each element in the compound or molecule. For example, for water, if we were going to find the molar mass of water, we would have to look up hydrogen. Hydrogen's molar mass, if you look on the periodic table, is 1. But notice, I've got 2 of them. So I'm going to add another 1. And then I'm going to add that to 1 oxygen. Now, oxygen on the periodic table is 16. So 1 plus 1 is 2, plus 16 is 18 grams. And that's how they got the molar mass of 18 grams. And that's 18 grams in 1 mole of water. So if you had 1 mole of water, it would have the mass of 18 grams. So a little bit more on molar mass. If we were to calculate the molar mass of carbon dioxide, again, you look up carbon, there's just 1 of them here. So we're going to take 12, and we're going to add that to oxygen. But notice, there's 2 oxygens here. So I'm going to put 16 plus 16. Okay? And that's what they do here. And they get 44 grams. Same thing I would have got. 44 grams. Okay, so what this means, in 1 mole of CO2, or carbon dioxide, which is 6.02 times 10 to the 23rd molecules of carbon dioxide, it would have a mass of 44 grams. Okay, practice problem number 28. It says find the molar mass for the following. There's a few parts on this, so let's just go through them individually. On A carbon atom, carbon has the molar mass of 12. If you look on the periodic table, it's 12 grams. Okay. Oxygen, look it up on the table, periodic table, it's 16 grams. Okay, CO2, we just did this one, but carbon is 12 grams, and oxygen is 16 grams, but I got 2 of them. So that's 32 plus 12 is 44 grams. Okay, so just add them up if it's a molecule. Sodium chloride, sodium is 23. And so we're going to add that to a chlorine, which is 35. see if I can do math. That's 8 and 5, so 58 grams would be its molar mass. Lithium oxide, lithium is 7 grams, and oxygen is 16. Okay, so 7 and 6, 13, so 23 grams would be its molar mass. And part F, this is a large molecule, glucose, C6H12O6. So I'm going to come up here and give myself some room. Carbon, we got 6 of them, and each carbon has a molar mass of 12. Okay. And so 6 times 12, just so I don't make any mistakes, is 72. Okay. Let's do hydrogen now. Hydrogens, I've got 12 of them. And each one, if you look on the periodic table, hydrogen is 1. So that's 12. And now let's do oxygen. I've got 6 oxygens, and each one, if you look on the periodic table, is 16. Okay, so 6 times 16 is equal to 96. Now, once you get them all totaled up for each element, we're going to add them all together. So 72 plus 12 plus 96 is 180. So 180 grams. If you had 1 mole of glucose, the mass would be 180 grams. So that's molar mass. Hopefully that's pretty easy. You probably remember a lot of this from last year. There was an extra practice. I think we're going to do this one. Let's try this one. So it says, how many grams of chromium are there in 0.045 moles of chromium? So that's what we're starting with. We're trying to go to grams. So I'm going to put 0.045 moles of CR and put that over 1. Okay? Now if you look at the roadmap, we're at moles. And we want to go to grams. So let's go on the bottom part, and we're going to take that top bridge on the bottom section there. But even if you didn't have a roadmap, you have moles of chromium on top. We know that moles of chromium have to go on the bottom. Well, in 1 mole of chromium, what's its molar mass? Chromium is Cr on the periodic table. Its atomic number is 24. So chromium is 52 grams per mole. And so 52 grams of chromium. Our moles of chromium cancel out. And now I just have to multiply across the top. So 0.045 times 52 is equal to 2.34. And that, my units are going to be grams of chromium. So if you had 0.045 moles of chromium, that would correspond to 2.34 grams of chromium. So, good job. Okay, I'm going to skip through the rest of these. And now let's go to a problem that involves 2 steps. So maybe we're going from mass to moles and then to particles. Notice there's not a shortcut that goes from mass to particles or vice versa. You always have to go to moles. That's almost always going to be our first calculation, is to go to moles. So let's try one. Okay, a party balloon contains 5.5 times 10 to the 22nd atoms of helium gas. What is the mass in grams of the helium? Okay, as always, I'm going to underline what it gives us, atoms of helium, and it wants us to know the grams of helium. Okay, so let's write down what they gave us, 5.5 e to the 22nd atoms of He. And we're going to put that over 1. Okay, now if we look at the roadmap, we're at atoms. Well, it doesn't have atoms on the roadmap, but atoms is in the particles circle there. So we've got to convert to moles first. Okay. If atoms of He is on top, we know that atoms of He has got to go on the bottom. We know that there's 6.02 times 10 to the 23rd atoms of helium in 1 mole of helium. So now my atoms of He cancel out, I'm to moles. So we just did that first step. But now it wants us to go to grams. And so we got to keep going. Let's do one more and go to grams. Okay, so if moles of He is on top, we know that moles of He is on bottom. In 1 mole of He, what's its molar mass? Well, helium on the periodic table has a molar mass of 4 grams. Okay, now my moles of He cancel out, and I'm left with grams of He. So we can stop there. Let's cross multiply across the top. So 5.5 times 10 to the 22nd times 4 is equal to 2.2 times 10 to the 23rd. Now let's go across the bottom. We got 1 times Avogadro's number times 1. So I'm going to put 6.02 e to the 23rd on bottom. And let's divide those two numbers. You should get 0.3, if you round it to 2 decimal places, 37. And what's my units going to be? Grams of He, grams of helium. So kind of interesting, a party balloon filled with helium would contain about 0.37 grams of helium. Not that much, but that's to be expected. This is a small balloon. Okay, good job. We're going to skip the extra practice problems here. Again, if you need help, come and talk to me. We can go through more. Okay, now we're going to get to the second part of this video, which is about stoichiometry. Stoichiometry is just a critical part of chemistry. So it's a skill that we just have to get down. I've got a lot of practice problems. We're going to explain a lot. We're going to go back to the basics of stoichiometry for a second. And hopefully this will catch on. You'll catch on to this. So stoichiometry, here's the definition. Stoichiometry is the study of quantities, which is amounts of materials consumed and produced in chemical reactions. I think stoichiometry is really cool because we can, if you know how much starting material you have, you can actually go through the calculations and determine how much of the product you're going to form before you even do the chemical reaction, which I think is amazing. Let's just go through it and see. So stoichiometry is based on the law of conservation of mass. The law of conservation of mass. So what does that mean? What that's saying is that mass is always conserved. So you can't create nor destroy mass. So if you started a reaction with 25 grams of reactants, when you do your reaction, the products better have a mass of 25 grams. So you can't create or destroy mass here. So it's always going to be conserved. So the mass of the reactants equals the mass of the products. Here's a practice problem, number 30, that deals with the law of conservation of mass. It says, consider this chemical reaction. And it says, what is the mass of the reactants? Remember, the reactants are on the left side of the arrow. So these are your reactants. And this side, the right side, is called the products. So if we look at the mass of the reactants, let's look here. We've got 4 irons. So I'm going to take 4. And iron, if you look at the periodic table, atomic number is 26. Its molar mass is 56. 56 grams. And we're going to add that to our other reactant. We have 6 oxygens. So I'm going to take 6 and times it by its molar mass of oxygen is 16. Okay? So let's figure out what the mass of our reactants would have been there. So 4 times 56, and add that to 6 times 16. I'm getting 320. 320 grams is what our reactants, the mass of the reactants. Okay? And then the second part says, what is the mass of the products? Well, let's look and see if it would be any different. How many irons would we have here? 2 times 2 is 4. So we got 4 irons times 56. And then how many oxygens would we have? 2 times 3 is 6. So again, 6 oxygen. So again, we're going to have 320 grams. What's cool about this is we started with iron and oxygen separated. They were just pure. And then we did our chemical reaction. We turned them into something and combined them into iron oxide, but they still had the same mass. The reactants and products still had the same mass. And that's the law of conservation of mass. You can't create or destroy it. There says 319 because they probably didn't round like we did with our iron and oxygen. So close enough. Okay, coefficients represent moles. The coefficient in a balanced chemical equation indicates the number of moles of that element or compound. So the coefficients tells us moles. For example, in this example we have 4 moles of iron. That's the coefficient, it's up front. So we got 4 moles of iron reacts with 3 moles of oxygen. The coefficient out front tells you the number of moles. And it makes 2 moles of iron 3 oxide. So that's how you would read that. Just remember that the coefficient out front tells us the number of moles. Okay, practice problem number 31. It says, in the chemical equation, in this chemical equation, how many moles of C3H8 would we have? Well, let's just look at the coefficient here. There's no coefficient. But in chemistry, a 1 is understood. So we have 1 mole. 1 mole of C3H8. Okay, part B, how many moles of O2 do we have? Well, we have a 5 as a coefficient, so we have 5 moles of oxygen. How many moles of CO2 are produced? We see a 3 as a coefficient out here, so that means 3 moles. Okay. And D, how many moles of water are produced? We see here we've got 4 moles as a coefficient, so 4 moles of water are produced. Okay, now let's move on to mole ratio. A mole ratio is a ratio between the number of moles of any 2 substances in a balanced equation. An example, this will make more sense as we go through an example. In this equation, it says, what is the mole ratio of potassium to bromine? So potassium has 2 moles, so I'm going to put 2 there. And it's a ratio, so it's a comparison of 2 numbers. And bromine has a coefficient of 1. And so that's our mole ratio, would be 2 to 1. Okay, what is the mole ratio of bromine to potassium bromide? Well, bromine has a coefficient of 1. Okay, and potassium bromide has a coefficient of 2. So that would be 1 to 2 mole ratio. Okay, what is the mole ratio of potassium to potassium bromide? Well, potassium has 2 moles, and potassium bromide also has 2 moles. Now, if you can reduce mole ratios, you can. And so since 2 is divisible by itself, that reduces to 1 to 1. And so the mole ratio there is 1 to 1. Okay, practice problem number 32. It says, determine all the possible mole ratios for the following balanced chemical reaction. Okay, and so to determine all the possible mole ratios, well, we could have aluminum to aluminum oxide. We could have oxygen to aluminum oxide. What other ones could we have? I guess we could have aluminum to oxygen and vice versa. And that might be it. So let's see if we can come up with these mole ratios. So aluminum to aluminum oxide. We've got 4 aluminums. Let me try the other spot, another spot on the board. So 4 aluminums to 2 aluminum oxides. Now this could be reduced to 2 to 1 mole ratio. Now let's do oxygen to aluminum oxide. Oxygen has 3 moles. Aluminum oxide has 2. So 3 to 2 is reduced as much as it can be. That's a small ratio. Now let's do aluminum to oxygen. Aluminum has 4. Oxygen has 3. And so it would be a 4:3 mole ratio there. So hopefully that makes sense. Mole ratios are pretty easy, but they're very crucial in the next step that we're going to learn. And so we have to know mole ratios. Okay, I think we'll skip the extra practice here. Now we're going to talk about using stoichiometry. This is a very important point here. It says that all stoichiometric calculations begin with a balanced chemical equation. It has to be balanced, or your moles are going to be off, which is going to throw your mole ratio off, which is going to throw your whole calculation off. So make sure it's worth your time to make sure that an equation is balanced. So it's easy. You've got 4 ions on the left side, 4 on the right. 6 oxygens on the left. 2 times 3 is 6 oxygens on the right. So take a second and make sure that it's balanced before you start anything. Okay, now we've made it to the point where we've got this whole roadmap. And I've given you a paper with this roadmap on it. We're going to use it a lot. And hopefully we get to the point where we don't need it all the time. I don't use it anymore, but it's useful to use when you're beginning learning the stoichiometry. So let me explain a little bit about this roadmap. Okay, on the left side, this whole entire left side area, this is for the reactants on your chemical reaction, and I call the reactants A. Okay, then we've got this arrow here, and that separates the products. The products are on the right side, so everything over here on the right side is products, and I'm calling the products B. Now, everything on this roadmap is the same. So what I mean by that is we've studied this part of the roadmap. Okay? And if you look, the other side is a mirror image of it. So we've studied this as well. The only part that we're introducing that's new is called the mole ratio. And you'll notice here, mole B, which means moles of product, all over the moles of A, which is moles of reactants. And that's if you're going this way on the roadmap. Notice down here, if you're going the other way, it's just the inverse, mole A all over mole B. I want you to write a note in your roadmap. There's numbers that go here. Where I just drew these lines, there's numbers. Where do you get these numbers that go there? You get them from the balanced chemical equation. So this mole ratio here, you have to get these numbers from a balanced chemical equation. Let's try a practice problem and see if we can make sense of this. Okay, before we do that, let's go through the steps involved in solving these problems. So I always like to follow these steps. Number 1, make sure that it's balanced. You write a balanced chemical equation before you do anything. Step 2, determine what is given in the problem. I always like to underline what is given. Okay, and this is where you're going to start from. This is like if you take your roadmap, I want you to look at the roadmap and say, where am I? And put your finger on where you're starting. Are you at moles of product? Are you at moles of reactant? Are you at grams of product? Or are you grams of reactant? Put your finger on it. Okay, it will help you. Step 3, determine what the problem is asking for. I always circle what the problem is asking for. And then I want you to look at the roadmap and say, where am I going to go? And put your other finger on where you're going. So you have one finger on where you're starting and one finger on where you're going, and then we can map it out. We can just determine what we need to times everything by and map out the calculations. Okay, remember, to go from a reactant to a product, so if we're going to cross that roadmap, you must first convert to moles of reactant and then use the mole ratio. You can use the mole ratio to get to the other side, to moles of product. Okay. Let's go through a problem. Practice problem number 33. It says balance the following equation. So let's just do this a quick method here. It looks like our nitrogens, we got 2 on this side. We're going to need a 2 right here to get our nitrogens balanced. But what that does to my hydrogens, we got 6 now. So I need 3 right there. So now we're balanced. Now we can do some calculations. It says if 3.5 moles of NH3, which is ammonia, are produced, how many moles of H2 were used? So we're starting with moles of ammonia, and it wants us to go to moles of H2. Again, let's just write down what they gave us, 3.5 moles of NH3, and put that over 1. Okay. Now, I want you to look at your roadmap. We are at moles of ammonia. Well, ammonia is a product. So we're at moles of product. I want you to put your finger on that part. And where is it asking us to go? To moles of hydrogen. Well, hydrogen, moles of hydrogen, that's a reactant. So we're going to go to moles of reactants. So put your other finger on moles of reactants. Now, we just have to do one calculation. Let's take that bottom bridge, which was mole A over mole B, and we've got it. Okay? So let's make one more conversion factor. And here's how you don't need the roadmap. If you just look, moles of NH3 is on top. It's got to be moles of NH3 or ammonia on the bottom. We know we're trying to go to moles of hydrogen, so I'm going to put that on top. Okay? Now, where do I get these numbers from? There's got to be numbers here. Remember, you get them from the balanced chemical equation. How many moles of NH3 or ammonia do I have? 2. I have 2 moles of ammonia. How many moles of hydrogen do I have? 3 moles of hydrogen. Remember, you get these numbers from the balanced chemical equation. Okay. Now my moles of ammonia cancel out, and I'm finished because I'm at moles of hydrogen, which is what it wanted. So let's just multiply across the top. 3.5 times 3 is 10.5. Multiply across the bottom, so 1 times 2 is 2. And so we take half of 10.5, and we get 5.25. And what's my units going to be? Moles of hydrogen. Okay. So let's look at what we just did there. I hope you appreciate what we are figuring out. If you want to make 3.5 moles of ammonia, if you want to make 3.5 moles of this, you better start with 5.25 moles of hydrogen. Okay. Practice problem number 34. Here's our equation. First of all, is it balanced? 3 ions. 3 ions. 8 hydrogens. There's 4. Oh no, those are oxygens, sorry. So 4 times 2 is 8 hydrogens. Okay, oxygens. We got 4 times 1, which is 4, and we got 4 oxygens there. So we're dealing with a balanced chemical equation. That's always a good thing to look at before you start. Okay, now we can do the problem. It says if 15 moles of iron oxide, so that's what it's given us, are produced, how many grams of iron must be reacted with excess water? So we're looking for grams of iron right here. Okay. So let's write down what they gave us. 15 moles of Fe3O4 and put it over 1. Okay. Now grab your roadmap. Let's look at where we're at. Where are we starting? Okay, we're at moles of iron oxide. So we're at moles of product. So put your finger on that. Where are we going? We're going to grams of iron. Iron is right here. So we're going to mass of reactants. So put your other finger on mass of reactants on the far right, bottom, or the far left, bottom left. So we've got to go from moles of products across to moles of reactant, and then to mass of reactants to solve this. Okay, so now we have it mapped out. Let's just do it. Okay. Well, if moles of iron oxide is on top, mole of Fe3O4 is on bottom, and we're trying to go to iron. So I know that moles of iron has got to go on top. Now, where do I get these numbers from again? The balanced chemical equation. It looks like we have 1 mole of iron oxide, and it looks like I have 3 moles of iron. Okay. Now my moles of iron oxide cancel out. I'm to moles of Fe. I can't stop there because it wanted to go to grams. So I need another one. Moles of iron is on the bottom. Okay. In 1 mole of iron, what's its molar mass? Well, if you look at the periodic table, it's 56 grams of iron, or in 1 mole of iron. Okay, so we can cancel out my moles of iron. I'm done, so I put on an equal sign. Let's multiply across the top and bottom, and we got it. So 15 times 3 times 56 is 2,520. Everything on the bottom, 1 times 1 times 1 is just 1, so that's not going to matter. And my units are right here, grams of iron. Okay. So if you were asked to make 15 moles of iron oxide, if you wanted 15 moles of this, you've got to start that reaction with 2,520 grams of iron. That's pretty cool to figure out. Before you even do it, we can figure out exactly how much we should start with. And that's why stoichiometry is so useful to chemists. Okay, practice problem number 35. It says in this equation, which is balanced, you can check it, it is balanced. If 23.5 grams of potassium are reacted, so that's what they're giving us, 23.5 grams of potassium, are reacted with excess water, how many grams of potassium hydroxide will be formed? So we're looking for grams of potassium hydroxide. Okay, let's line up the calculations here. So we're starting with 23.5 grams of potassium. Potassium is just K. I'm going to put that over 1. Okay. So now let's look at the roadmap. We are at grams of potassium. So grams, so that's mass of a reactant. And we are going to go to grams of potassium hydroxide. Potassium hydroxide is right here. So we're going to go to mass of a product. So we're going to go all the way across the roadmap, from the bottom left to the bottom right. So now that we have it mapped out, let's continue on. Grams of K is on top, it's got to go on bottom. So in 1 mole of potassium, how many grams do we have? So that's molar mass, let's look it up. 39. 39 grams of potassium in 1 mole. Okay, now my grams of potassium is gone, cancels out. I'm to moles of reactants now. Now I got to go across the roadmap to moles of product. If moles of potassium is on top, it's got to go on bottom. The product that we're going to is potassium hydroxide. So that's going to go on top. Now where do I get these numbers from again? The balanced chemical equation. You notice we have 2 moles of potassium and 2 moles of potassium hydroxide. We could keep it 2 to 2, and I'm going to in this case. But if you kept it 1 and 1, if you reduced that mole ratio to 1 and 1, it would be the same thing. Okay. So my moles of potassium have canceled out. And now I'm to moles of potassium hydroxide. I can't stop there though because it wants to go to grams. So I got one more conversion factor to go through. If moles of KOH is on top, I know it's got to go on the bottom. In 1 mole of KOH, what is its molar mass? Okay, well let's figure that out. Potassium is 39, so I'm going to take 39, add it to 16, which is oxygen, and 1 for hydrogen. So I'm getting 56. So 56 grams of potassium. Let me make sure I did that. I'm going to do that again. So 39 plus 16 plus 1 is 56. Okay. So now I'm at my moles of potassium hydroxide cancel out. I'm at grams of potassium, which is what it wanted, so I can stop. Okay, let's just multiply across the top first. So 23.5 times 2 times 56. I'm getting 2,632 divided by, let's multiply across the top. So 1 times 39 times 2 times 1 is 78. So now let's divide those. So 2,632 divided by 78. Okay, and this is what I get, 33.74. 33.74. What's my units? Grams of potassium. So, pretty cool what we just figured out there. If we started this reaction with 23.5 grams of potassium, we are going to end up, I'm sorry, this should be potassium hydroxide. So I forgot to put the OH there. So potassium hydroxide there. We're going to end up with 33.74 grams of potassium hydroxide. So that is what's so useful about stoichiometry. Okay, extra practice if needed. Yeah, we would go through these in class if we need it. So I'm going to skip through them here. Okay, I think we'll stop there in the video. We'll pause there. You've learned enough to do another assignment in your student workbook. So if you'll open up your student workbook, you now know enough to do the mixed stoichiometry worksheet. The mixed stoichiometry worksheet. So take a moment and see if we can get those done. Good luck.